All right, let's go ahead and start. I have the attendance going around somewhere. Okay, so some of you asked about the video for Facebook. If you don't know, I'm talking about week 7, which is next week. There's a video due, and I don't care if you do that in a group or whatever to make it better. Sometimes by yourself can be a little lame. Lame. When you're trying to take a video of yourself here, you know. Yes. No, you don't actually have to be in it, but you need to be like part of it, like part of the filming or something. Oh yeah, that's fine. That's fine. And are you narrating it? Okay. That's fine. I'm just seeing what her thoughts were. Okay, yeah. So just somehow, I want you to make some sort of inspirational chiropractic video. And if you want to do that by yourself, like she's doing a picture collage of real people. And she's going to show it, apparently. I don't know if it's to music, but maybe. We'll find out. It's a surprise. And I don't care. You're not limited to anything. You can work in a group to make a good one. But it only needs to be like 2 or 3 minutes. I mean, I'm not talking about, full-length feature film here or anything. But just to kind of put your whole Facebook thing together, why is chiropractic amazing to you, And why should it be amazing to me too? Does that make sense? So something like that. And if you have any questions or if you're wanting to know if something will work, because she just asked me about the pictures. If you have, just email me or you can come see me if you want to know before you do it if it's appropriate or not. So these should be fun. Have fun making them. So that is your final Facebook thing. And that's going to be actually due not this Sunday, but next Sunday at midnight because I have to have them graded by Monday to get your grades in. So you don't have quite as long to do it, a full week like normal, and that's what I'm going to tell you today. Okay. Yeah, so that's what's left with Facebook, just the video there. All right. So let's go over our amino acids. Let's just look at the last ones we saw yesterday. I think we started with tryptophan. Tryptophan has this indole ring, which is the benzene connected to this nitrogen ring. This functional group is called an indole. And this one's tryptophan. This is the one we see in turkey. And this produces, or in the body, it's converted into melatonin, and that's what gives you that sedative effect. We started looking at the polar uncharged. So polar is meaning it has an electronegative atom in there. Uncharged meaning there's not a charge. We looked at serine, which is just basically methanol, which is a CH2OH coming off. This one has hydrogen bonding. And since alcohol is a decent nucleophile, it can further react. We also saw threonine, which is kind of like an isopropyl with the alcohol. And the same thing as hydrogen bonding. And because of this alcohol, as a nucleophile, it will further react. This one's essential. And the last one was cysteine. This is your thiol with the SH. This can form your disulfide bonds, which are in your hair. Disulfide meaning 2, right, or di. So basically 2 of these join together at the sulfur there. Okay, so we're going to do 4 more today, and then 3 more Monday, and then we're done. Okay? How many? 20? 20 on, well, there's not going to necessarily be 20, but you're responsible for 20. There will not be 20. But I'll choose randomly. Okay, the next one, asparagine. What functional group is right here? Amide. Yeah, the carbonyl with the amine, which is the amide. This one can further react because of the amide and actually grow an amino acid chain. So all amino acids can join together at the carboxylic acid right here. But this one can also join at the amide. So it has two positions that amino acids can join, which is pretty unique. Most amino acids can't do that. There's actually 4 total that can do that, and this is one of them. Does this one have hydrogen bonding in the R group? Here? Yes, with the NH2 right there. It can hydrogen bond. And sort of like its older brother, there's glutamine. The only difference between glutamine and asparagine is glutamine has an extra CH2 group. So this one's CH2, CH2 amide, and the one asparagine is just CH2 amide. So there's just an extra carbon in there. So it's almost identical to asparagine, has the amide, it can hydrogen bond, and can also further react with other amino acids. Glutamine's interesting. It can help pH balance in your kidneys. So if you're having like a kidney infection or something, it could help with that. It's also been known to reduce healing time in wounds. Yeah, there's 2. So they're like in a chain. Yeah, so it's in a chain. So it's like CH2, CH2, amide. Yeah. Yeah, it's going down. Okay, now we have the positively charged groups. Now these are positively charged in the body. So outside of the body, these are actually neutral. But after they've reacted, they have a positive charge. So these are positive charged, also basic amino acids, which sounds counterintuitive because it sort of is. But again, this is after it reacts. So what does a base do? What does it grab? A hydrogen. So this is showing, for example, this amine right here, which is basic, after it's reacted as a base. Okay? So after it's reacted as a base, it has a positive charge. So that's why they say basic with a positive charge, because it's after it reacted. So this first one's lysine. This one's essential. Now this one, it has 4 CH2 groups in the NH3. And so let me show you here. When they have that with the parentheses 4, or sometimes you'll see it with a 2 or whatever it is, do you see that it's in a chain like this? There's 4 CH2s connected together. Lysine smells pretty bad because it's one of your amines. And this is supposed to help with collagen production. And then our last one of the day. And then only 3 more after this. Not too bad. Arginine. This group right here, do you see I have an NHC, NH2, NH2 is sort of a strange group. That's called a guanidine. And that's Guanine. And the guanidine looks exactly like this. This is the guanidine functional group. What's interesting about arginine, for those of you who want to know, it is used a lot of times with erectile dysfunction. So you can write it down and star it just in case, no judgment. But arginine has been shown in several studies to help with that. If you want, yeah. Well, this could help though, even if it's not yourself, for patients, if they want a more natural way to help with erectile dysfunction, arginine can help. So, okay, that's it for the day. Well, for amino acids. All right, so let's look over amines. So the first reaction we looked at was this one. All right, do you remember what happened in this reaction? So let's look at this. The nitrogen, so we're in the amine chapter, okay? Where would this want to make a bond? The carbonyl, which causes those electrons to go up. All right, now let's look here. I have a negative and a positive. How can they neutralize each other? Take a hydrogen. Yeah, this oxygen here is going to take a hydrogen right there. Now, do you remember the final step here? Okay, OH is going to leave, but what does it leave as? Water. So it's going to grab a hydrogen. And what will help that to happen? Heat, but in the mechanism. Here, these electrons right here will go down, which will kick off the OH to grab the hydrogen. So the final product is this. Oh, yeah. There you go. So if we look overall, what happens, is this the carbonyl oxygen, is it on there anymore? No. What does it leave as? Water. And what replaces it? The nitrogen. And the nitrogen started with 2 hydrogens, and where did they go? To the oxygen to leave as water. So remember this reaction. We'll see it again in the new reactions we're doing today. Okay. So all we're doing here basically is this group minus your hydrogens will take the place of oxygen. Okay, then we also looked at, let's see, a Huffman elimination. Okay, what happened here? What does the first step do? What? Yeah, how many methyl silicon? 2, yeah, because it wants a total of 4 carbons on there. How many carbons is it currently attached to? 2, so it's going to add 2 more to get the 4. So in the first step, I'm going to add 2 methyl groups. So this allowed this nitrogen to be a good leaving group. Now, hydroxide is a base, so it's going to take off a hydrogen. And what will end up forming in the final product? A double bond. So we need to figure out where we're going to form the double bond. So we look at all the carbons the nitrogen is attached to. Do we need to worry about the methyls? No, because you need 2 carbons to make a double bond. We can look at this one because there's more than 2 carbons, and we can look at that carbon right there. Now between the 2, the left and the right, which one is less crowded? The one on the right, because it's smaller. Okay, so this is where the double bond's going to form, and what will everything else do? Leave. So when we draw our final product, the nitrogen there is the leaving group, and then this part is the double bond. I'm going to show you this before we go on, because I think it's interesting. So this is the synthesis, or the partial synthesis, I should say, of Lipitor. Do you know what Lipitor is used for? Yeah, we've seen the commercial. Cholesterol. It's lower cholesterol. When was this article? This was like maybe 2003 or something like that. And that year alone, it made $10.3 billion from just Lipitor. Okay. People do not want to just lose weight. They just want to, take a pill. But it's okay. Whatever. That's their problem. So we need to look at how to synthesize it, because that's why we're in here. So here's where they actually start out as isoascorbic acid. This is our starting material, okay? But we're going to skip ahead a few steps and look at the ones we know. Okay, so looking at this right here, what is NaBH4? What does that do? Reducing agent. And is it a weak or a strong one? Weak, so it'll only reduce what? Well, it's a type of carbonyl, 2 types of carbonyl only. Aldehydes and ketones. Those are your least reactive. So aldehydes and ketones there. So I have a ketone right here. And NaBH4 is a weak reducing agent, so it's only going to reduce the ketone, not the ester. So do you see here? It reduces it to an alcohol, which is what a reducing agent will do. Carbonyl goes to an alcohol. This next step here, this one's a little bit harder to see, but this is kind of similar to our protecting group that we use, the one that looks like that. Okay, this is just a different protecting group, but it's still a protecting group. And what this one will actually protect is the alcohols, okay, because we don't want them to react. So protecting group is there to protect whatever the most reactive group is, in this case the 2 alcohols. So it protects. Now, here, now the ester is going to react. Now, if I put ester, what's my leaving group? I mean, I circled it, but this O carbon group in an ester is always the leaving group. Now, if I react this with water, what do you think will replace it? A what? An alcohol, an OH. Usually when you have water reacting with something, you're trying to put an alcohol on there. So do you see right here? I now have an alcohol on the ester. Okay? Now, how do I take a protecting group off? Like H3O plus. H plus with H2O, that is H3O plus. This equals to H3O plus. So you see H3O plus takes off the protecting group. Anyway, several more reactions, you create this. But I just wanted to show you, so you can kind of see the point of these reactions is to make this stuff here. So these, again, the reactions you're using in class or something very similar are what they're using to make $10.3 billion. Okay, so it's a huge industry that I'm teaching you. I promise that it is for a reason. So. You're in the wrong field, right? 10.3 billion. Yeah, work on that one. Forward. Maybe you need to go back. All right, let's do the Cope rearrangement. All right, this is very similar to the Hoffman. Okay, what does peroxide, hydrogen peroxide, what does that do to an amine? Puts an oxygen on there. Like this. And then your nitrogen will be positively charged. And what do we call a positive and a negative in the same compound? Zwitterionic. So now if nitrogen is a positive charge, it's a good leaving group. It wants to leave. Okay, and I have this oxygen that wants to neutralize itself. It's going to act as a base, taking off a hydrogen. So I need to decide where can I take the hydrogen off of. It's going to form the double bond just like the Hoffman. So do I need to look at the methyls? No. So I can look, I can go here to here or here to here. So the right or the left? The right. So it's always the shorter side with the less branching. So you're going to come over here. You'll take off the hydrogen, leaves its electrons, and what leaves? The what? No, what you're leaving. Well, you're form the double bond, but what leaves so you can form it? Not water? The whole entire nitrogen group. So that's your double bond. Or nitrogen is a good leaving group, so the whole entire, everything connected to nitrogen will leave with it. So N, CH3, CH3, and now the oxygen will be an alcohol since it took off a hydrogen. Let me... So again, on the sapling, there's some good ones on there to practice with these. If you can do the ones on sapling, you should feel pretty confident that you understand these. They're a little bit more challenging, but they're challenging is fun, right? So try those out. And then the last one we learned yesterday Okay, so that carbonyl is called an acid chloride. You can recognize it because it has the chlorine. And in that functional group there, what is always our leaving group? Chlorine, and what will replace it? The nitrogen group, yeah. So the chlorine will be gone, and now I'm going to have NH, and that's connected to that carbon group too. It'll always be one hydrogen short because nitrogen, to be neutral, only wants 3 bonds. So carbon, how many bonds does carbon want? 4. Oxygen, do you know how many oxygen wants to be neutral? 2. Think of a carbonyl. How many bonds does it have? 2, and it's neutral. And then nitrogen wants 3. So if you look on the periodic table, it goes carbon, nitrogen, oxygen, and the bonds go 4, 3, 2, and if you want to look at fluorine, it's 1. Okay? And those are the number of bonds it wants to be neutral. So if it ever has more or less than that, you have a charge. So nitrogen, how many does it have coming off of here? Including the hydrogen, 3. And so if I would have left that other hydrogen on there, I would have had a positive charge. Okay, so to look at the new reactions, we're going to skip some of these. Hoffman. Okay, so don't worry about the, well, that part is fine. But don't worry about the acylation of aromatic amines. Don't worry about that. Here. Don't worry about diazonium salts. So we're going to start where it has alkylation of amines. Do you know what it means when it says you're going to alkylate? What is an alkyl group? A what? What? Not trouble. It's an alkane. It's just a carbon group. So we're going to alkylate an amine. So what does that mean? We're going to add a carbon group to an amine. Okay? Anytime you see alkylation, that'll come in biochemistry also. Alkylation just means you're going to add an alkyl group, which is a carbon group. Alkyl, just alkyl in general, just means carbon group. Usually when we look at alkyl groups, typically we're looking at single bond carbon groups, but I've seen them use it very loosely to any carbon group. Okay, so we've kind of done something before. Do you remember in the Hoffman where we had the amine and we put the alkyl halide in there, like CH3I? The problem with that is that you can't stop it adding carbon groups. It's so reactive. Remember that we had one before over here. We're trying to add this carbon group to it and it ended up adding 2. Okay? And if that carbon group wasn't there, I would have added 3. Okay, so you can't stop this reaction. It's not, I mean, if that's what you want to do, like for the Hoffman, this is great. But if you're trying to just add 1 carbon group on there, this is a terrible way to do it. Okay? So I'm going to show you a good way to do it. What is the show called? Which is the one with the chemistry teacher and Breaking Bad. Okay, so he uses these reactions to make his methamphetamine. Now I'm not going to show you how, but he uses reductive amination to do those reactions. So now you can go back and watch them, and you can actually understand somewhat what he's talking about there. Here, so the first one, and I'm going to change this just a little bit so it makes a little bit more sense. Okay, so we could have let's just start with step 1, and I'll write step 2 down in a minute. Okay, so this one, do you remember the first reaction we did today where we had the amine react with the carbonyl? Okay, the carbonyl left the oxygen, and what did it leave as? Water. Okay, and then what took its place? The nitrogen. Okay, and that's what's going to happen here. So the nitrogen will come in, attack the carbonyl, the electrons go up, okay, now, how can I neutralize this? Grab a hydrogen. This is your final product there. So what do I do? How do I get to this? You're going to push the electrons down, and then OH leaves and grabs one of the hydrogens. So you see, it's the same exact reaction for this first step. So the first step in making meth is this. Okay, so this is the exact same reaction we did before. Okay, I didn't change anything. Now there's a new step we're going to add. So this is a reductive amination. So when they say reductive, what do you think of? Reduction or reducing. So what do you add when you're reducing? Hydrogen. So the second step, let me start right here. So this is just that. I'm just redrawing it. Okay, and if I put in there lithium, aluminum, hydride, and usually some acid in there. Okay, so this is a hydride. This is like a negative charge hydrogen. Do you see that this is kind of like a carbonyl? It's called an imine. And it's going to attack it just like a carbonyl, causing those electrons to go up. Okay, now in the final product we don't like to have charges. So we have an acid in there in step 2. So what will that nitrogen do? It'll just grab that hydrogen. Okay, so looking at this, let's look what we just did here. Now, in the original, let me write it all out together here. So this is this in steps. So the first thing we did was add NH3. Now, NH3, does it have any carbon groups on there? No. Now, at the very end, my product, after I add NH3 and I reduce it, okay, do you see where the carbonyl was? That's where you're going to add your NH2. There's not a double bond there because remember we reduced it. Now, on this nitrogen, how many carbons is it attached to? 1. So you just added 1 carbon group to the nitrogen. So it went from just a regular amine, it's not really, it's not a primary, to a primary amine. So it's a way to add 1 carbon group. So if we look at this one, let's see if we can predict it. That's a nitrogen connected to a methyl and 2 hydrogens. There we go. Okay, so let's just look at our final product. Now, where will this nitrogen be connected? Where the oxygen is, the carbonyl. And will it have a single or a double bond after we reduce it? Single bond. The carbon groups, if there's a carbon group on the nitrogen, it will stay on the it will stay there, okay? So it will be connected to a CH3 for sure. Now looking at this, now you always have to kind of decide, well, how many hydrogens we have off of it at the end. How many bonds do I have to nitrogen right now? 2, and how many does it want to be neutral? 3, so you'll have your 1 hydrogen there. So that's your final product. Now let's look right here. This nitrogen originally was what type of nitrogen? Primary. Now it is a secondary. So basically this reaction will add one additional carbon group. And the carbon group it adds, do you see like down here, for example, where the carbonyl was attached? That's the carbon group it adds. Or if we look at the one above it, this carbon group there. So basically all of the carbons coming off the carbonyl, you will now attach that to the amine. And then let's look at one more to make sure you have this down. Okay, we look at our original amine in step 1. What type of amine is that? Oh, this one here, primary, secondary, tertiary. Secondary. So after this reaction, what do you think it'll be? Tertiary. We're going to add one more. Okay, so where do I add my nitrogen? Where the oxygen is. And it will be bonded how? Single bond. And what will be coming off of there? Two methyl groups. Do I need any hydrogens coming off of there? No, because it's already neutral. When you have that down, we could take a break. I'll look up. I'll show you what they do in Breaking Bad. I don't want to look it up on that computer to red flag everything. But I'll put it up. I'll pull it up on my phone and I'll write it down here to show you. So you can see a practical application of reductive amination. So, all right. So let's take a break. All right, let's go ahead and start back up again. All right. This is the reaction they use in Breaking Bad. Did any of y'all watch Breaking Bad? Okay. What do you think this is? They talk about it all the time. Methylamine. They're always trying to get a hold of methylamine somehow. Okay, so we have methylamine, and we're going to react it with the ketone here. It what? No, this is, well, I mean, it's the same reaction we've been doing. But no, you do not have to memorize how to make methamphetamine. Yeah. So what would we do here? Where would we connect the nitrogen? To the carbonyl. And it would be connected by what type of bond? Single bond. And how many carbon groups connected there? One right here. How many hydrogens? One. And there you go. That's it. It's not as impressive, right? No. Okay, so those are your reductive animations. If you look in the notes, they kind of do it as like 3 or 4 different reactions, but it's just the same reaction. It's just the difference is how many carbons originally on your nitrogen, okay? But it's the same thing happens. The last reaction I'm going to go over in this chapter is this. So we already know this part of the reaction. What happens in this reaction here? Cl leaves and is replaced by NH2. So that part we already know. We learned earlier. We learned yesterday, actually. But we can reduce this down. Now, amides can reduce down further than like esters and all of those. So think about what we did up here. This is just another way to do a reductive amination. Now, in the end, all we did was add 1 carbon group to nitrogen, right? That was the purpose of this, okay? So our original amine, how many carbon groups were on it? 0. And now how many carbons is it attached to? 1. But we don't want a amide, we want an amine. So what do you think this will do to the carbonyl? Completely gets rid of it. It's kind of like the Wolff-Kishner reaction. So you see the carbonyl was right there, and it just erased it, it's gone. And so now I've added 1 carbon group to the amine. So it's just another way of doing it. And that is it for chapter 19. And that's the end of exam 4 material. So on Monday, we'll review. Okay, so when is your 19 sapling due? Tomorrow, okay, so you'll have it done. So we'll go over anything you had trouble with there. Study over the weekend. Let me know if there's anything in particular you're having trouble with. I can do specific examples like those. Okay, so we'll review the second half Monday. Yes? Yeah, it's one of those. It's either the Cope or the Hoffman. I think they're both similar. And don't worry, we're not done for today. we're going to learn about some carboxylic acids. But we only have a lecture and a half left. Well, the ones that I'm going to give you. Sapling. Do you remember the number it was?
I think it was 5.
If I pull it up and you saw it? This one? Okay. So let's look at this. Let me actually draw it. So do you see that the nitrogen is actually inside of the ring? That definitely makes it more challenging. This one already has enough carbon groups on it. Basically, it's already reacted it with methyl iodide, so you don't need to do that. So do you see the hydroxide right here? That's your base, and we're heating it up. So they're just looking at the double bond portion of this. So let's analyze this nitrogen. Now let's look at all the carbon groups it's connected to. Do I care about this methyl? Or that methyl? No, so really we're going to look inside of the ring. Okay, so mark, put a dot, whatever you want to put, every carbon that you care about that nitrogen is connected to. So we don't care about the methyls because they're not long enough to matter. So it's connected to this carbon and that carbon. Okay, now to make the double bond, you have to go one more carbon away. So what we're saying, these two carbons here possibly could be one of the carbons in the double bond. Now the other one, you go one more away. So you go here to here. I'm going to put an X. Here to here. Put an X. And is there another one? Here to here, right? Now, out of all of those, we'll say 1, 2, 3. Which one looks the least crowded? 3. Now, also consider here, so I'm going to break this bond right here. All right. Now, do you see that this nitrogen is still connected to this carbon? Okay. So I'm just breaking that bond. I'm not breaking that bond. So when I do this, so where's my double bond form? Yeah, so it's between the X and the dot. Okay, it's always between X and dot. So and then here's my hydrogen, my base. We'll pull it off there. Make the double bond right there, like we said, which breaks this bond and moves the lone pair to nitrogen. So when we draw this, we have nitrogen, carbon, carbon. Like that. Now if I put in, I'm going to kind of dot where it was. It was connected right there, right? I kind of put a dotted line. I don't know if you can see it. But it was connected there. But that's the bond we broke. But do you see that nitrogen is still connected overall to everything? That's because it's in a ring, you'll always have this because it's connected twice in there. Does that make sense? So look at the other one. I think it's very similar. If I remember correctly, I could be wrong, but I think it's also in a ring. Which is so this is number 5, and so I believe the next one's number 6. So see if you could do that one, later on your own. So knowing how to do this one. So again, what you do, you put dots on all of the carbons that matter connected to nitrogen. So that would be this one and this one. And then from there, you have to put your X's, which are the next carbon away. All of the next carbons away. So it'd be that one, this one, this one, this one. So your double bond is always between the dot and the X. Okay. So let's look a little bit at carboxylic acids. What is a carboxylic acid? What does it look like? Yeah, carbonyl OH. Sometimes you see these written as just COOH, shorthand, instead of actually doing the double bond O connected to the alcohol. So if you see COOH, that means carboxylic acid. Aliphatic acids, those are just carboxylic acids with a long carbon chain connected to it. Okay. And your fatty acids, that's a really long chain connected to a carboxylic acid. Okay, so naming these will end in oic acid. So for example, we can look at this here. How many carbons in this chain? 1. How do we name 1? Yeah, like methane. So this would be methanoic acid. So keep the whole name like methane, but drop the E. So methanoic acid. Let's look at this one right here. See, there's 1, 2, 3, 4 carbons. So what would that be? So butanoic acid. And then how do we name this right here? Methyl, right? And so that's on carbon 1, 2, 3. So your carboxylic acid will always be carbon 1. If we look at the one above it, whenever you're naming, you try to include as many functional groups as possible. So the longest chain here with all the functional groups is 1, 2, 3, 4, which again would be butanoic acid. So this is our chain, that's butanoic acid. Do you remember how to name a carbonyl that's a branch? Oxo. So this would be oxo, and then what do you call this with 3 carbons? Propyl. Which one comes first alphabetically, oxo or propyl? Oxo. So we have your carboxylic acid is always carbon 1. So 1, 2, 3 oxo, 2 propyl butanoic acid. The new branch we'll kind of learn today is your amine. An amine as a branch is called an amino. So if we look at this one, what's the longest chain here? 4, which would be butanoic acid again. And what do we call this? Amino. And it's coming off carbon 4. let me just explain this right here because this can come up in biochemistry, so at least you've heard it before. So this is your carboxylic acid. This is your main functional group here, your most reactive. Now instead of just going 1, 2, 3, 4, for whatever reason, biochemistry has their own numbering, sort of. And so 1 away from the functional group is called alpha, and then beta, and then gamma. I usually don't go past gamma. But you see this is the sign for gamma because it's in the gamma position. Now if you look here, don't ever count the carbonyl carbon. So it's alpha and then beta. So the B is the Greek letter for beta. Anyway, so if you ever see that, and so like this one's alpha for the A, 1 carbon away. So if he ever talks about alpha, beta, or gamma, that's just how many carbons away are you from that functional group? Okay? Oh, that's just a common name for that. Don't worry about the common name. Like, for example, this one's formic acid. This is acetic acid, but the proper name for it, like the IUPAC name, is ethanoic acid. So this is just like slang, sort of, if you want. Also in naming, we have our benzene. So if we had an alcohol coming off benzene, what is that called? Phenol. And what if you have an amine coming off benzene? Aniline. And then so a carboxylic acid coming off benzene is benzoic acid. Benz meaning benzene, oic acid meaning your carboxylic acid. And so we'll just look at one of these here, or two of them actually. So here, this is your benzoic acid. This part right here, benzene with a carboxylic acid. And what do we name this right here? Amino. And it's 1, 2, 3, 4. So you could say 4 amino benzoic acid, or how they have a name is para amino benzoic acid. Same thing. And I just want to show you this one because this comes up in your lab for 10. So this is your benzoic acid. Do you remember how to name an alcohol as a branch? Hydroxy. So do you see so benzoic acid, and then you could say 2-hydroxy benzoic acid or ortho-hydroxy benzoic acid. And this is salicylic acid. This is one of your starting materials to make aspirin. So that's the naming. So again, naming, it ends in oic acid, and the new branch we learn is amino, which is your amine. And I just want you to know, if you see a dicarboxylic acid, it's just a dioic acid. So just recognize like the name at the end. So an oic acid is just 1 carboxylic acid. If you see dioic acid, that means there's 2 carboxylic acids. Okay, so the structure of these. This carbon here has a double bond, so it's sp2 hybridized. Does a carboxylic acid have hydrogen bonding? Yes. So is that going to make the boiling point higher or lower? Higher. So carboxylic acids have pretty high boiling points. They also have resonance. I mean, you can move the electrons around. So this lone pair can move there, which would cause this double bond to move up as a lone pair. This comes in. This is what makes it acidic, actually. So we'll look at it in a slide, but so here's a carboxylic acid, And what does an acid do? Gives up a hydrogen. So after it reacts with a base of some sort, you get this. Now, do we like to have charges? Are those stable? No. So what carboxylic acid can do, what makes it acidic, is that it can stabilize itself because it can move those electrons there, which causes those electrons to move up. So when you do that, you get this. So basically you move the double bond to the other oxygen. Now the point of this, there's still a charge on there. You're not going to get rid of it until you react it. But the reason this is good is because now you're sharing that negative charge between the two oxygens. You have the ability to do it. Anytime you can share a charge, you're not as reactive. The product, I should say, is not as reactive. So if a reaction is going to occur, you usually want to move towards stability. So this product has the ability to stabilize itself, which is kind of weird, makes this more reactive. So if your starting material can stabilize itself in the product, it'll make this more reactive. So that's why it's acidic. It's acidic because the product can be stabilized. Let's look at substituent effects. A few of these, we talked about that. Okay, let's look at this. So a lower pKa means what? Is it more or less acidic? More acidic. Okay, now let's look at this here. The difference is the number of chlorines we add. So this one has 0 chlorines on it. This one has 1, 2, 3. What's happening here? Is it getting more acidic or? Yes. What happens is that, okay, so after these react, that oxygen right here will have a negative charge. So this oxygen, this is the hydrogen that'll leave, leaving you with a negative charge. Okay? Now, if you can stabilize a negative charge, it's better. Chlorine is an electron withdrawing group. Okay? So it's going to withdraw electron density. So I have a negative charge. Think negative, it has to do with electrons. Okay? So if I'm withdrawing that from it, it's stabilizing it. Okay? Now, if I donate electron density, that means I'm putting more negativity into it, making it less stable. But in this case, I'm withdrawing it, so it's not quite as negative. Okay? So chlorine is an electron withdrawing group. It takes away some of the negativity and puts it on itself. So do you see how this one has 0, so the pKa is 4.74. This has 1, and so the pKa drops to 2.86. Add another stabilizing group, and it's now at 1.26. Add 3 of them, and now it's at 0.64. So basically, now you have 3 chlorines that can take away some of the negativity. Now, what's the difference down here? So they're getting more acidic as we go to the right. Why? It's closer, yeah. Think about it just in terms of magnets. Can you feel the strength more when you get closer or further? Closer. So the same thing here. These are going to have more of effect the closer they are to that negative charge. Okay? So the more chlorines, or it's really any halogen, the more halogens you have, the more acidic, and the closer they are, the more acidic. These right here, whenever you have like 3 chlorines on there, those are sometimes called superacids because they're very acidic. And it's the same thing here. So, all right. This is just showing you that carboxylic acid is an acid. So as an acid, you have a base. Base takes off a hydrogen. Acid gives up the hydrogen. So at the end, don't worry about this M right there, that metal. But in the end, you have this oxygen with a negative charge because it gives up a hydrogen. That's what an acid does. And the reason I show you this, I think it's in the next slide. Not there. Sort of. Okay. These are called carboxylates. So you'll see this, I've mentioned this before, in biochemistry. So a neutral carboxylic acid, before it's reacted, is a carboxylic acid. You react it, and it loses its hydrogen, has that negative charge, and this is called a carboxylate. 8, anytime you see 8, that usually means a negative charge there. Now in the body, so the pKa of a carboxylic acid is around, we'll say 2. Okay? What is the approximate pH of your body? 7.4. So is your body more or less basic than a carboxylic acid? Way more basic. So as soon as you put a carboxylic acid in your body, it turns into a carboxylate. Because it's, what does an acid do? It loses its hydrogen. Okay, so a lot of times in biochemistry, they refer to these as carboxylates, which basically is your carboxylic acid after reacted. Because in biochemistry, we're looking at mechanisms and reactions inside of your body. Okay, so just know, if he talks about a carboxylate, that is just a carboxylic acid with a negative charge. Okay. Properties. Let me just show you this so you can see kind of a practical application here. So soap, like the old-timey way to make soap, you would get either a big thing of fat or oil, and you'd hydrolyze it. Okay? So what functional group is this? So I have a carbonyl O carbon. Ester. That's the ester. So you see I have 3 esters all connected together. Carbonyl O carbon, carbonyl O carbon, carbonyl O carbon. Okay? Now, anytime I react something with water, what functional group does it usually add on to there? OH. Okay? Now, this is showing in basic conditions, so of course it's not showing me with the OH. But this is your OH right here. Use your imagination if you want. Okay? Now, what was my leaving group? So I put my OH on there, and look at this. Basically, this whole thing here, the O carbon group. Okay? So one thing you're going to learn in chapter 21, let me show you these. I like chapter 21. It's very simple and straightforward. I think you'll like it too. Okay, so looking at all these carbonyls, okay, this is your acid chloride. This is your amide, ester, carboxylic acid. Now, there's a difference in reactivity and everything of these, okay? And you'll learn about which ones are more or less reactive. But another big difference between those, what I'm trying to get at, is the leaving group. What's the leaving group for an acid chloride? Chlorine. What do you think the leaving group for an amide is? Here, NH2. What's the leaving group for ester? Look at the trend. OR. What is the leaving group for carboxylic acid? The alcohol. So basically, do you see how the left side here, I'm drawing it to the left, it doesn't have to be to the left, but do you see how this side here is the same? I could just put R there if you want, because it could be anything. But what makes each carbonyl unique, that's the leaving group. So what makes a acid chloride different from a carboxylic acid? This has the chlorine. This one has the alcohol. Okay, so the part that makes it unique, that's your leaving group. So if we look over here, this O carbon group, that's the part that makes ester unique. That's the part that'll leave. Okay, and what replaces it in this case is OH. And that's all you have to do. You get your fat, your oil, put it in basic water, and it will create a soap. Okay, so let's look at saponification, which is just making a soap. Some important acids you might have seen or heard of. Acetic acid, which is just vinegar, diluted acetic acid. Your fatty acids, which are in your body. Benzoic acid, it's used in a lot of drugs and preservatives. Adipic acid, this makes nylon 66. Pantyhose and stuff. Phthalic acid, this uses polyesters. These are a little bit outdated for our time, or not so much for other people. But you've at least heard of them. All right, so those are some common carboxylic acids you might have heard of. Okay, a carboxylic acid in the IR is very easy to see. You're going to get the carbonyl, which comes in around 1700. And then you also have the alcohol, which is that really broad peak. So these are pretty easy to spot in an IR, because you'll have both of those peaks. Like right here. So here's your peak at 1700-ish. And then right here is your giant alcohol peak. NMR, the one thing that stands out in NMR for carboxylic acid is this alcohol off the carboxylic acid comes in between 11 and 12, and is the only peak that comes in at 11 and 12. Okay? So if there's not a peak there, you do not have a carboxylic acid. If you have a peak between 11 and 12, it could only be a carboxylic acid. So using NMR or IR, they're very easy to spot. Okay, so let's look at review a few reactions, and I'll let you go. These we've already seen before. So let's look at the bottom one here. It's one you've looked at. If I have a primary alcohol, what is this right here? What do I have a lot of? Oxygen. So this is the oxidizing agent. Is this strong or weak? Strong. How many times can this be oxidized? Twice. So what will it turn into? Carboxylic acid. I'll give you a hint. This is a carboxylic acid chapter, so the answer to really anything I ask you is carboxylic acid. Okay? So do you see this CH2 right here? This is what turns into your carboxylic acid. KMNO4. This is the bad surgeon. And what does the surgeon do? Cleaves and caps it with oxygens. Now, what does it turn into alcohol? Like, coming off here, can R groups turn into an alcohol? No. What can't? The hydrogens. So on the right side here, will that turn into a carboxylic acid? No, but the left side? Yes, because you have the hydrogen. Of course, it doesn't show it very well. But your hydrogen turned into a OH. So how they're showing it here, So you have double bond R, cap it with oxygen. That's one side. What does that make here? This is a ketone. And then the other side with R, and then my hydrogen turns into an OH. What does this make? Carboxylic acid. So you need a hydrogen off of there coming off the double bond to make the carboxylic acid. All right, then we also looked at this one. Okay. So we're using KMNO4 again, which is still a surgeon. But now we're going to react it with a triple bond. So what do you think it'll turn the triple bond into always? Carboxylic acid. So it's going to cleave it. And basically at both ends, so do you see I have R, C, C, R, there and there. This carbon, the carbon that was a triple bond, turns into a carboxylic acid. Does it make sense which carbon is the carboxylic acid? It's the two that are actually part of the triple bond. So a triple bond does not need a hydrogen. It will always turn into a carboxylic acid. But a double bond has to have the hydrogen off of there to turn into a carboxylic acid. So that's the difference. And then one last one, and then we're done. And it's another one we've done before. Again, using KMNO4. So this is benzene with a carbon group coming off. So this is from chapter 17. Do you remember what this does to that R group? Turns it into a carboxylic acid. So it cleaves the whole thing off, essentially, except that first carbon, and turns it into a carboxylic acid. So this could be, I don't know, a lot of carbons long. That doesn't matter. It all cleaves off, and you just draw your carboxylic acid. And that is the end.